let's get started. Welcome to the second webinar, the second GeekGap webinar. And today the schedule is as follows. So unlike the previous one, we are just going to have algorithm and data structures today. So, and the focus for this webinar will be on recursion. And I prefer to have just an algorithm data structure webinar instead of both algorithm data structures and system design, because recursion is such an important topic. So I would rather have us spend a full session, a full webinar on recursion and try to understand it as much as possible. Because most of the time in doing interviews, technical job interviews, you're going to get recursion problems. Sometimes disguised, and sometimes obviously there will be recursion problem. So we're going to discuss first of all what is recursion, and we're going to have a framework that we're going to follow on how to solve recursion problems. So, and that framework we're going to use for five different case studies in order to approach recursion problems. And finally, we're going to have a closing remark on different variants of recursion. So without further ado, what is recursion? So recursion, as Wikipedia defines it, is a method of solving problem where the solution depends on solutions to smaller instances of the problem. So here is the key. So when we are talking about recursion, like the definition says, is that let's say we want to compute, for example, for this problem here, let's say we want to find the size, the disk size of this path. Using recursion, what you're going to do first is you need, in order to get the size of this, so to get the size of this folder, you need to get the size of all his children first. So you need to get the size of this one, the size of this, the size of this. And really, it's the same problem, because if you zoom, for example, here, in order to get the size of this guy, you need to get the size of this, you need to get the size of this, and so on and so forth. So really, that's what recursion is. So once again, you're asked to find the size of this folder, but before getting the size of this folder, you need to know the size of its children. And when you're here at this child, in order to get the size of this child, you need to get the size of the grandchildren, and so on and so forth. So this is a very intuitive example in order to explain what recursion is. So the approach that we're going to follow, the general pattern that we're going to follow to solve recursion problem is the following. We're going to solve in 3 different steps. First of all, we want to find the smallest or easiest instance of the problem that we want to solve. And next, we want to break original problem into sub-problems and assume somehow that we had a magical function to solve those sub-problems. And finally, we are going to combine the solutions to the sub-problems in order to find the solution to the bigger problem that we had. So let's try to do this in our example that we have for finding the disk usage of a path. So here, what could be the smallest instance of this problem? So I can think of 1 or 2 cases. Maybe like one of the smallest case could be finding the size of a file, right? Because if you're at the file, if it's a file, then really all you need to do is to get the size of the file, get the size, because since it's a file, you don't have to, you don't have any you don't have any children, so you can directly get the size. So this is the smallest instance of the problem that you can have. Now, what about breaking the problem, the original problem, into sub-problems. And we already touched on that earlier in our previous slide. So if you are to get to solve this guy here, we can break, this is our problem, right? We can break this problem into smaller problems. So we can have a sub-problem here, a sub-problem here, a sub-problem here, and a sub-problem here. So really what you want to do is, if you're asked the size of system, the part called system, what you want to do is to get the size of all the children of system, individually. So this may give you maybe, I don't know, 2 megabytes. This may give you 3 megabytes here. This may give you 5 megabytes, and so on and so forth. And this may give you 10 megabytes. So you have the size of each individual problem. Finally, what you want to do is to combine the solution that you've got for the sub-problems. And what you do now is you sum the size of all the children plus the size of system itself, because in some file systems, folders have size as well. So, and this is how you combine the solutions to the sub-problem in order to solve the original problem. And this is a very common pattern in computer science, so much so that it has a specific name. It's called divide and conquer. Divide and conquer. So you have here, when you're getting the sub-problems, you're actually dividing your problem into sub-problems. You divide, and this is at the second step. Here you divide. And finally, here you conquer. And this is a computer science pattern that we're going to follow for each of the case studies that we're going to see. So first of all, let's move to a demo. I'm going to show you how we can implement this. Great. So what we're going to do, this is the disk usage function that I wrote here. And we're going to follow these steps using the debugger. And I'm going to run this using the debugger in order for us to understand what is actually happening. So here, I just run the function. And what is happening is that when we hit this line, then we got line 29, because obviously it's not a file at the beginning. So this condition here, we test if it's a file. Remember the base case. We first test if it's a file. If it's not a file, then what do? We get the size of all the children. And this is what we are actually doing in this loop here. And for each child, for each of the children of this size, of this path, we call the function recursively. So see here, we call this function. It's like a function calling itself. But here we pass in a different parameter. So you can see here, this child path is something different than the path that we had here. And you can see it's a sub file within this path. You can see it's a sub folder inside. So if I go to the next step of the debugger, you can see now that the current path is dstore, which is a file. So we enter the base case and so on and so forth. So now we are out again and so on and so forth. So do you follow? So it's really recursive, and each time each time for each children, we compute the summation, the size, and we accumulate in this variable here, children size. And once you're done, I won't follow all the steps because there are quite a lot of files in this folder. So at some point, we are going to hit this line here, and this will means that we have we have all this we have found all the size the size of all the children within a single folder, and then we're going to get out like this. So if I close this and I actually run the function, you're going to see what it's going to write here. You can see here that it gives the size and it gives the path. So you can see for each of the so it enters here, it computes, and so on and so forth. This file in particular has a size of 0. It goes out, and this is what is actually happening. So I'm going to move back to the slides. Okay, so as you can see, this is the solution that we just saw here on the slide again. And now, is there any question before we move? Is the concept of recursion clear, intuitive enough? Because now we're going to move full speed to case studies one by one. And these are, believe me, problems that you get doing software engineering interviews. So these are real examples, real problems that you get during interviews. So if there are any questions before we move to them. All right, I assume no question, and hopefully you have questions when we are going to move to the other ones. First of all, factorial. So write a recursive function to compute the factorial of a number. So first of all, when you get a problem like this, your first task as the interviewee is to understand the problem. So you may come to the interview without knowing what the factorial is. And if that's the case, it's perfectly fine. Just ask your interviewer, what is factorial? Then he will say something like, factorial is the function defined such that equals to 1 if n is lower or equal to 1 and is equal to n times factorial of n minus 1 or otherwise. So he will define the function like this. And once this function is defined, it's quite obvious that it's actually a recursive function, because in order to know factorial of 5, for example, you need to know factorial of 4, and so on and so forth. So what about the easiest instance of the problem that we can have? So the easiest instance, we can see 2, and they're already given in the problem definition itself. So when we have factorial of 0 is what? Is 1, because the problem says if n is lower or equal to 1, then it's 1. You return 1. Factorial of 1 as well is equal to 1. So these are the easiest instances, and what we call the base case. The base case. Base case. And here in this instance, we have actually 2. Now we break the problem into sub-problems. How do we do this? We break the problem into sub-problems. Well, the definition of the problem is already giving us what we have to do, but the subsequent case studies, it won't be the case. So, okay, so here we have factorial of n. If we want to know factorial of n, we need to know factorial of n minus 1. We need to know. So this arrow here means need to know. We need to know this. Need to know this guy. And let's assume that magically, somehow, we have this solved for us. Let's assume that we have this. Let's assume that fn minus 1 is given. Because assuming that allows us to move on to the next step, which is actually computing fn. So if we know f of n minus 1, what does it take for us to compute fn? Well, it's simple as doing n times f of n minus 1. That's it. And that is as simple as that. And if we move back to the implementation, you're going to see once again how this operates. Just let me know if you see my pie chart again. Let me move to factorial. Do you see the factorial function? Hello?
Yes.
All right,
Yes.
great. So if I run this in the debugger, for example, here, you can see for n equals 0, obviously it's going to go out. So we are running this within. So if we pass in here, we are here, we pass in n equals 0, it enters here obviously because it's lower than 1. So it returns 1. And what about computing f of factorial of 5? Well, for factorial of 5, it doesn't enter here directly. So what it does, it first computes f of 4. You can see here in the debugger. So in order to know that, here we were at this frame, we were at factorial of 5. But factorial of 5 needs to know factorial of 4 first before moving on, before actually reaching here. So, and factorial of 4 needs to know what? Factorial of 3, and so on and so forth, up to the point where you reach the base case. And once you're at the base case, you don't need something else. So the base case is self-sufficient to solve the problem. So if you have the base case, you can directly return, and that's what's happening. And you can see now that we are at the base case, we can now sum up. So the base case, so when we have factorial of 3, we computed factorial of 2, and factorial of 2 returned from the previous one. So here we move on, and you can see this, all the results are now accumulating in order to give us the final answer that we need. You can see here, this is factorial of 5, waiting for factorial of 4 to come to finish, and factorial of 4 needs to get his response from factorial of 3, which is this guy here, which is previous factorial. So we are going to return. So when we will be in factorial of 5, which is still waiting for factorial of 4 to finish, previous factorial will now be what? 24, because it will be 4 times 6. So let's do that, you see. Now previous factorial, because factorial of 4 is done. So now we are at factorial of 5, and we're going to do 24 times 5 in order to get the final answer. And you can see here that everything was computed fine. And one thing I want to draw your attention on, because we're going to look at that in the next slide, I'm going to do this again for factorial of 5. As you can see here, the stack is growing, right? The stack is growing. So here we try to compute factorial of 5, 4, and 3, and 2. We keep adding things here. This is what we call a stack trace. So, and this will help us in order to understand the memory complexity of recursive algorithms. So here, when I run this again, you can see we have 1, 2, 3, 4, 5, 6 things in our stack frame. In order to compute factorial of 5, we have 1, 2, 3, 4, 5 things in our stack trace. And once we have solved the smaller problems, we now remove things from the stack trace back. And let's move again to our slides. Okay, we already did the coding time, and you can see here, this is the solution, and this is the time complex, not the time complexity, but the timing that we have for this. And look at these numbers, especially in the next slides, the next case studies, because at some point we're going to compare bad and good implementations, and these numbers are going to help us. So let's try to find the time complexity of factorial. So again, factorial is defined as, let me get another color. Okay. Get this one. Great. So factorial is defined as f of n equals to n times f of n minus 1, right? This is the definition of the factorial. So we want to know how long it takes in terms of how long it takes, the time complexity, when we are passing an argument of an integer n to that function, how long it takes, because you saw here, it grows with the size of the input parameters. So for example, here, when we say factorial of 1,000, it takes 3 milliseconds. When we say factorial of 4, it takes 7, or you can say 8 microseconds. So how can we mathematically assess the time complexity? Because guess what? In technical job interviews, you're not just asked to write a solution like this, but also to give an analysis, an assessment of how long your solution is taking. So what can we do? So we can say that from this formula, we can say that the time to compute the time it takes for an argument n to compute the factorial will be the time to compute n minus 1 plus a constant time. Why? Because doing a multiplication, if you had, let's say, if you had a times b, this is a constant time operation, right? But if b was also variant, like if b is depending on your input parameter, which is the case here, then you need to add the time it takes to compute that additional parameter. That's why we say constant time for the multiplication plus the time it takes to compute f factorial of n minus 1. And doing this by proxy, we can say that the same thing for t of n minus 1. What can we say about it? It's t of n minus 2 plus c plus another constant. It doesn't have to be the same, but for sake of simplicity, we're going to just call it c as well. And same thing, like vice, you can say it's t. I'm going to just put one brace because I'm sure you get the idea, just to make it simple on us. So t of n minus 3 plus c plus c plus c, which is what? Which is 3c. If we continue doing this, at some point we're going to get t of n minus k plus kc, right? And the time complexity that we actually know is the time complexity of 0. So we know that t of 0 is equal to 1, or a constant, preferably, because t of 0 is given to us. So we want to express t of n in terms of something that we know. And let's say that because the more we go, at some point we're going to reach t of 0, right? So if we are t of 0, it means that n minus k equals 0, which means that n equals k. So let's do that here. We can say equals to t of 0 plus nc. This is a constant, right? It's not necessarily the same, so we can call this c prime and n of c. And this is why we say that this is a linear. From this, you can deduce that this is a linear algorithm. This is a linear problem because this is big O of n. So your solution, your problem is linear in time. Your problem is linear. What about memory? What about memory complexity? Well, we saw that in order to compute fib of 5, for example, we needed to keep in the stack trace fib of 4, fib of 3, fib of...
Junior?
Yes?
Sorry, I'd like to take you back a bit.
Yeah, sure.
Is that okay? Let's talk about why the function is linear again. Could you take me through that again?
Oh, absolutely, absolutely, great. So let me start from scratch here again. All right. Yeah, sure. By the way, interrupt me if you don't get something. It's better like this. So let's do that again. So we have Fibonacci, factorial of n defined as n times factorial of n minus 1. That's the definition, right?
Mhm.
That's what we have. We want to know the time it takes to compute this guy, right? And
Mhm.
we know that in order to compute this guy here, in order to compute this, we need to compute this first, as the definition goes. So the time to compute this will be function of the time to compute this guy. Do you follow so far? So
I follow.
yeah, so we can say that the time to compute n will be what? Will be equal to the time it takes to compute n minus 1
Times n.
plus a constant time. We can say that we can call that constant c, because here what you have here is each operation, like when you are at f of n, let's assume, because we said let's assume that magically somehow we had this already, right?
Mhm.
Let's assume that we had this. What will it take? What will it take for us to find what is the amount of time it will take in order to find f of n? If f of n minus 1 was given to us, it will be a constant time because it doesn't depend on n anymore. And it's the time it takes to do this multiplication here. It's the time it takes to do this multiplication. So this multiplication happens in constant time. Constant time. Both, we, because we have to take into account the time it actually took in reality to compute f of n minus 1, we have to say that the time complexity to compute t of n is equal to the time complexity of the multiplication, which is this factor here, plus the time complexity of n minus 1. Do you follow so far?
So c is a constant. C is basically t of n.
C is...
Sorry,
Yeah?
c is the constant.
Yeah, C is a
The time it takes to compute factorial of n minus 1 times n, correct?
C is the time it takes for doing the multiplication here.
Yes.
Yeah. And f minus 1, t minus 1, t of n minus 1 is the time it takes to find f of n minus 1.
Oh, okay. It's okay then.
Great.
Continue.
Yeah. So now that we have this, we continue like this. So, and we do the same thing. So now we have a formula to find the time complexity of n based on the time complexity of n minus 1. So once we have that, what we do is we have now t of n minus 2. We can do exactly the same operation. We can say this guy here, t of n minus 1, can be reduced as plus another c. And you keep the previous one here like this. And which gives you t n minus 2 plus 2c plus 2c, right?
Yes.
You do the same for n minus 3. So so the time it takes for you to compute n minus 2 is the time it takes you to find f of n minus 3 plus a constant plus the 2c that you had earlier, which altogether will be 3c,
Interesting.
right? And now if I follow these steps, at some point I'll reach t of n minus what? Minus n, because I'm increasing up to some point. I'm going to reach t of 0, which is what? T of 0, which is really t of n minus n, right? Plus, if I follow the pattern, it will be nc. And this is why we say that, and t of t, which is, this is what? T of 0, because this is 0. So it's going to be t of 0 plus nc. And t of 0 could be another constant that we can call d. And now we have a formula. We have an estimation of the time it takes. So we know that if the problem is of size n, if our problem is of size n, like here, the time it takes to solve this problem is linear. It's a linear function of the size of your original problem. So it means that if you had a plot like this, I'm going to write here and then erase back. So if you had, what this means is, if you had a plot, if you have a plot like this, and this is n, and this is t of n, so the size of your problem, it's a linear function like this, with a slope equals to c, the constant time. So it means that if your problem takes, if you give a problem of size 10, the time it takes to solve that problem will be 10c. So this is why we call this linear algorithm. So this is the time analysis of this problem, and we say the time complexity is linear. So now if we
Okay.
move, is it clearer now?
Yes, it is. It is.
Brilliant, brilliant, brilliant. So now let's move to the memory complexity of this problem. So remember when we were looking at the stack trace of the problem, we saw something very interesting. We saw that when we were computing factorial of 5, because we cannot just jump to the solution, we have to somehow find factorial of 4 while waiting for factorial of 4. The computer has to store this somewhere, right? So this is stored while we are computing this guy, the guys down, 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 right? So it means that this is already taking one space in memory, one store location. If we continue like this guy, to compute factorial of 4, we actually need to know factorial of 3, right? And while we are busy doing factorial of 3, we need to store this guy as well. So this will take one additional. So this will take 1 plus 1. Now we have two memory slots. And if we continue, if you have factorial of 3, we need to find factorial of 2 first. And while we are busy doing that, we need to
Takes
store,
another slot.
yeah, we need to store this guy, and so on and so forth. If you follow the pattern, you see that at the time we reach factorial of 1, let's say, how many slots have we stored? How many? It will be, obviously, it will be 5.
4. Yeah, 5 slots, sorry.
5, right? So it means that the memory complexity is linear. So it grows with the size of your problem. And this is inherent to every recursion problem, really. Is that recursion, by the way it is, inherently forces you to use a stack trace in order to store temporary results, temporary steps, because those steps can be proceeded unless you have the children. So because of that, the memory assessment of um, recursive problems is actually most of the time linear. So it's very important to know this, because sometimes you have two versions of the same algorithm, as we will see. You can implement some algorithms iteratively, you can implement some recursively, but if memory is an issue for you, and if you have to choose between the iterative approach and the um, recursive approach, you better go for the iterative approach, and we will have an instance of that, especially when we'll be talking about binary search and tail recursion and stuff like this. So without now, let's move to the question time. I think you already asked your question, but if you have any more question, feel free to ask.
None at the moment.
Great, great, great. So let's move to the next case, which is recursive power. Recursive power. Okay. So here the problem statement is, we want to write a recursive to compute x to the power of n with n greater or equal to 0. So what does that mean? It means that we want to find power, recursive function power, such that if you pass in a number x, we want to find the power of x to the power of n. And this is a function that's quite obvious, but we want to do this recursively. We want to implement the power function recursively. And one thing, like in order to understand, for example, this problem better, we can give ourselves a few examples. So if x, let's say x equals 2 and n equals 1, what should we get as an
2
output?
to the power 1.
Which is 2. Great. If x equals 2 and n equals 3, we want to get, which is 8. If x equals 2, n equals 0, we want to get 2 to the power 0, which is 1. So we follow the same pattern that we normally do. We find the smallest, easiest instance of the problem. And my gut tells me that it's actually this guy. So if we have the smallest, problem, smallest problem when n equals 0, because we actually have nothing to do, because all we have to do is just return 1, because by convention, anything to the power of 0 is 1. So that's it. We have our base case. Now, let's break the problem into sub-problems and assume that we had a function to solve those sub-problems. How can we break this? And we're going to see two ways. Let's see first a way that will yield a linear solution. And then we're going to see another approach that gives us a logarithmic solution. But first, the linear solution. So let's say we define power, we break the problem as follows. And this will show you that actually the way you break the problem down into smaller problems, it has a direct implication on the complexity, the final complexity that you get for your problem. So x to the power of n, we can define it as follows. We already have our base case above. We can say it's equal to 1 if n equals 0 from our base case here, and it's equal to what? X to the power times power of x and n minus 1. That sounds plausible, right? Because if you're doing 2 to the power of 5, we can do 2 to the power of 5 minus 1 times 2. And this is precisely what this function is saying here. Does that make sense?
Yes, it does.
Yeah, so that's how we actually break the problem into smaller problems. Because here now, this problem is what? Is 2 to the power of 4 times 2. And this is it's a smaller problem compared to this guy here. Now you broke your you have divided your problem into smaller problems, and you just assume that somehow magically you had a solution for this. You had a solution for this. Well, if you have a solution for this, all it takes to solve the original problem is to do what? Is to find is to do x times power of x n minus 1. And this is all it takes. This is how you're actually going to combine the solutions finally at the end. So when you break your problem, I shouldn't have written that formula here. I should have just written something like this. So power of n minus this depends on power of x and n minus 1. This is what I should have written, because now what I wrote before is actually combining stuff. But here we just want to find the relationship, how we can break the problem. So we are saying here, given what we just draw here, and what allows us to understand that 2 to the power of 5 can be broken down into 2 to the power of 4 times 2. Then we have this relationship that 2 to the power of 5 depends on 2 to the power of 4, and which is what we just wrote here. Once we have power of x n minus 1, how can we combine that solution to the sub-problem in order to find the solution to the original problem? Well, all it takes is to multiply x by the solution that we had for the sub-problem. And that's precisely what we're going to do now at the recording time. Great. I assume you see my screen again. So recursive power. Do you see my screen?
Yes, I do.
Great. So we are going to do the same exercise, just run it in the debugger and see what's happening. So 2 to the power of 0, we are here first, right? This is where our debugger is pointing. So we are here, we enter the function. Now we are here because it's to the power of 0. So we're going to return what? 1, because that's what the definition says. Now we move to 2 to the power of 4. What should we do? Well, in order to compute 2 to the power of 4, when we arrive here, guess what? It's not yet 0, so we're going to move here first. We come here, and then we enter, and we are now at the next iteration, because now we enter the function. Here, this is power of 2, 4. So x is 2, n is 4. But in order to find this guy, we need to find 2 to the power of 3. So, and while doing that, you see, this guy is taking some space in the memory. It's in the stack trace, waiting for us to compute this guy first. When we're here, 2 to the power of 3, we need to find 2 to the power of 4 first. So if I go, you see, we add something else to the stack trace, which is finding 2 to the power of 2. And now we add something else, which is 2 to the power of 1. And finally, 2 to the power of 0, which is going to return 1, which is the base case. So we have the base case. The base case is the case that doesn't need to be broken down into smaller pieces because it's the smallest pieces you can have. And once you are the base case, you can now move up, you can now move back on the stack trace and solve all the problems that you have accumulated so far. So now here we are the smallest problem possible, and that smallest problem possible is needed to solve this guy, which is x to the power of 1. Once we hit that, you see the smallest, the previous power is now what was returned by the smallest problem, and then we continue, we're gonna keep removing things from the trace, from the stack trace, until we get 2 to the power of 4. And now we are 2 to the power of 5, but I guess we don't need to do this because we have understood from the power of 4, which is pretty much the same thing. And really that's it. That's what you have to do to write your own power function in a recursive way. So I'm going to move back to sharing the slides again. Great. So you see, this is the solution that we had, we just saw. And you can see the time that it takes here. You can see 2 to the power of 2000 is giving us this. And look at this number carefully, because when we will look at the optimized version, which is the version just following, just after this, we're going to see that 2 to the power of 2000 is going to be a much lower number compared to this one. But first, let's do the time complexity analysis. And it's going to be pretty much the same. So I'm going to go quicker on this one. And if you have questions, just ask. So we are asked to do power. I'm going to call this power of n, xn. Let's do that cleanly. Okay, power of xn. And we want to find the time complexity. And it's defined as x multiplied by power of xn minus 1, right? It's pretty much like the factorial that we just saw. We want to find t of n, which is the time it takes if we have the power is n. What do we do? Well, it's like we saw before. It's a constant time, which is the time to do the multiplication. The time it takes to do this multiplication will give us c here, plus the time it takes to find this guy, which is t of n minus 1. And then you have your formula again. And like we saw earlier, this will give us Cn, which is, we can say is big O of n. This is how we find the time complexity. And the memory complexity, again, like we saw in the previous slide, is also linear time. So we can say time memory complexity is also linear time. Right. So that's it for the time and memory complexity for this. Let's move to the optimized solution for this problem. Well, we saw that before the previous version. What we did in order to find the small problems, what we did was t of n was P of n, sorry, power of n was defined, power of xn was defined as power of x and n minus 1. And that's what we had. But we can do better. What about defining power of x as 1 if n lower or equal to 1 and x times, this is power of x xn. All right, x, so x times x if n is even, and defining as if n,
Junior.
yes.
Wow, I dropped off like 3 minutes back.
Oh, really? Let me, so let me start over this problem, this one here. So let's do this. Let's do it like this. So here we saw that the time complexity and memory complexity for the power function, the way we defined it, is linear, both time and memory.
My expectation is it will be, yes, they will both be linear from what
Yeah, exactly.
I noticed. It was similar to
To the
Factorial.
factorial. Yeah,
Yes.
exactly. So, but in the specific case of the power function, we can do much better. We can have a better solution because for the power, the way we defined it is it's really up to it's really boils down to the way we defined it, the type of sub problems that we found we got here. We could have done a much better job, and let's see how. So remember previously we did this equals to 1 if n equals 0, and then x multiplied by power of x n minus 1. This is how we defined it. And this almost forced us to have a linear solution. But guess what? We can do much better. If we defined it instead like this, if we said p of x n equals to 1 if n equals 0 and x to the power of n divided by 2 times x to the power of n divided by 2 if n is even and x times x to the power of n minus divided by 2 if n odd. Does that make sense?
Hmm.
Because let's see how. If you have to compute, let's say 2 to the power of 4,
4.
it's the same as doing, instead of doing 2 to the power of 2 times to the power of 3, and then 2 times, which is what? 2 times 2 to the power of 2.
I get it now.
Yeah, you
I
could
get
have,
it now.
you could do directly 2 to the power of 2 times 2 and times 2.
Times 2. Yeah.
Right? But the good thing is, when you're doing it this way, when you're computing, you don't have to compute 2 times. You can just compute this guy once, and you just square it, right?
Yeah.
So you don't have to compute this other guy. You can just do like this. You can just do equals to 2 to the power of 2, and then you square it, which means that you can cut your problem by half and every time. So instead of going linearly, before what we did was linearly. The way we reduced the problem was linear. We don't do it like that anymore. We reduce the size of the problem by half each time. And this allows us to go much quicker, much quicker. And you can see here, if you look at the time it took for us, for example, to compute 2000 again, here, 763 milliseconds. And for here, it takes only 35 milliseconds. And because this implementation is logarithmic, and let's see how. By drawing, I should have added some space in order for us to draw that, but let me do it here, somewhere here. Let's see why it's actually logarithmic, the time complexity. So, right, so we have now a problem which is defined as power of xn will be a variant of power of x n divided by 2, right? Does that make sense?
Yes.
So it means that if you do the same, this guy itself is a variant of x by 4, which is depending on of x by what, 16. So if we do this, it means that actually the time it takes to find a power when the power we're looking for is n is a constant plus the time it takes to solve the problem of half the size. Does that make sense?
Yeah.
Because you still have that multiplication that you have to do. Now, if you do it again, c, it will give you plus another c plus t to the size of n minus 2, 2 to the power of 2, right? Because this is 2c. And if you do now, it will give you c plus 2c plus c plus t n divided by 2 to the power of 3, which is, this guy here is 3c, right? If you follow these steps, so on and so forth, what you get is kc plus t n divided by 2 to the power of k, right? You just follow the steps. Because here we have c to the power of 1, 2c 2 to the power of 2, 3c 2 to the power of 3, and kc 2 to the power of k, right?
Okay.
And what we know, what is something that we know, because we want to, at the end of the day, we want to to get this guy as a variant of something that we know. What we actually know t of 1, which is a constant time. So if we plug, if we had this guy, let's say, because at some point, because we keep reducing the problem by half, at some point we're gonna have a problem of just size 1, right? Because if you keep dividing something by 2, 2, 2, 2, 2, at some point down the line, you're gonna have a problem of just size 1.
Yes.
Right? So once we have that problem of size 1, it means that n 2 to the power of k equals 1, right? Which equals to n equals 2 to the power of k. And it's this k that you're looking for, right? Because we know that when we are at this step here, for example here, we have already done 2 steps in our attempt to solve the problem. When we are here, we have tried 3 steps in our attempt to solve the problem. When we are here, we have tried k steps in our attempt to solve the problem. So what is that k? We have that k when we have the smallest possible problem, which is the problem of size 1, which is this guy here. So this formula equals,
Continue.
yes?
Oh, it's okay. It's okay. Continue.
Yeah, so it means that k equals to, we can say, if I put the logarithm both sides, log 2 of n equals to k log 2 of 2, which is k, right? Do you follow?
Yeah.
Yeah, so it means that the time complexity, because actually we are looking for the number of steps it takes for us to solve the problem. So the number of steps it takes for us to solve the problem is k equal log 2 of n. So the time complexity we say here is k equals to log 2 of n. And this is our time complexity for this problem. And you can see it's much faster because if you draw a plot, let's say n and tn, a linear function grows like this, whereas a logarithmic function almost plateaus. It plateaus very quickly. So logarithmic function grows very slowly. And that's why you can see this time difference here, actually. When we have this implementation, the power optimized takes 35 milliseconds, whereas
Jesus Christ.
this other guy here takes 763 microseconds, sorry, but in terms of microseconds. So do you have any question?
None at the moment.
Great. Oh, and by the way, I think I said something which is not very correct previously regarding the memory complexity. The memory complexity usually is it's function of your time complexity for a recursive problem. If you're not using any auxiliary data structure to save the data while solving your problem, it's the memory complexity of recursive problems equals to the number of steps, actually, because at each step you need to keep something to save it because you need it later on. So because when we are computing this guy, we need to store this. We need to when you're trying to find this guy, since we don't know this guy here first, we need to save this operation
Are
in.
you moving your mouse? Oh, it's okay.
Sorry?
When you're trying to find the 35 sorry, when continue.
Okay,
Sorry.
great, great. So does that make sense, the time and memory complexity for this problem?
Yes.
Great. Let's move to our other case study, which is one that I really like because it's something that's, yeah, you will see. So now our problem statement here is to write a recursive function to reverse a list in place. What does that mean? First of all, the important terms. So it's always very important to try to understand the problem very carefully. So if you don't know, it's always important to ask the interviewer, what does in place means? Well, in place means if if you're asked to solve a problem, solution, and then input to give an output, in place means that your solution should not change. You're not allowed to change, do not change input. Oh, sorry. Um, if you're actually not allowed to do the thing in place, because here we're actually allowed to do it in place. But if your solution doesn't allow you to do the changes in place, what it means is that you cannot change the input parameters. Do not, oh wait a second, do not change. And an example for this may be you may want to sort the list. So you may have a list like this, 5, 3, right? And in order to make your life easier, in order to solve the problem, you may want to sort it first. But actually doing that, if the problem doesn't allow you to change things in place, you cannot do such a thing. But actually here we are even forced to do things in place. So I'm going to erase this, move to the actual problem understanding again, now that we know what in place means.
Sorry, this is probably a dumb question, but
Yeah, sure.
why not just create a separate array and append to that array? I'm not
Yeah,
edit.
here
I'm not.
what we want to do is to do the thing recursively and in place. So like this problem could be given to you in order to assess your algorithmic thinking. So it's not that we want to absolutely write the perfect solution. It's just,
Mhm.
this is an understanding problem. It's for us to understand recursion.
Okay.
So this is more of a didactic problem for us to, pedagogical problem in order to understand what recursion is. And bear with me, you will see it's quite insightful. So let's say our list was something like this. L equals to 1, 2, 3, 4, 5, and close. The problems, let's add a few more. 5, 6, right? So the problem says reverse this list in place. So at the end of the day, what we want is L is for L to look like this. 6, 5, 4, 3, 2, 1. Are we on the same page?
Yes.
Great. So this is the problem statement. We are both on the same page. We are all on the same page. It means we understand what the problem is, what it is that we are asked to do. We follow our same pattern for solving recursive problem. The first thing that we do is to try and solve a few instances of the smallest possible problem that we can get. Well, one of the smallest one that we can get is a problem of size 0. If there's nothing in the list, there's nothing to do. So if L is this, at the end of the day, it's going to look like this. Likewise, if L is just one element, there's nothing to do. You just have to return the sequence, actually. So these are the two smallest problems that you can get. So these are called the base cases. Now, let's break the problem into instances of smaller problems. And this is quite interesting, this example here. Well, how can we do this? How can we break this problem in terms of smaller problems? You see, sometimes it's not obvious how you can use recursion to solve a problem. But let's assume somehow that someone gave us how to solve this part. So let's assume that magically this part is given to us. What are we left to do?
Place 6.
So yeah, if this part was solved, so if this smaller L was solved for us, all that is left is to swap these two guys, right?
Yeah.
So we can say that we can define L if we have, let's say, if we call this boundary, let's have boundaries. Let's call this boundary here A and this boundary here B, right? If our list starts at A, boundary A goes till B, the sub-problem could be a problem L such that L starts at boundary what? A plus 1 and at boundary B minus 1. Are we on the same page?
Yes.
So this is precisely what we're going to do. And once we have that, this is the smallest, this is the relationship. So we have L, and if you assume that magically somehow someone gave you the solution to this, then you're good to go. you're good to go. You're absolutely fine. You can move on and actually combine the problems now. And by combining, we just have now to swap, um, you just have to swap position A and B from the original list. So now you swap A elements at positions A and B, and that's it. That's all there is to it. And let's see the code. Coding time. Right. So we are at what's the name of that problem? Where is it? Reverse recursive. Great. So let me close this guy. Let me put some okay, so and also for this one, we introduced the concept of helper functions. You saw, in order to solve the problem, we needed those boundaries, guys, right? We needed those boundaries, but these boundaries will not be given to you. Like this is our reverse function here, and like the person trying to reverse a list doesn't want to know about our implementation details. He doesn't want to know that we have those boundaries, we have these, but actually they're useful for us. Hence, we need a helper function to solve the problem, because those boundaries are the guys that are actually guiding, like telling us which problem to consider one after the other. So we start at boundary 0 at the very left, and boundary length of our array -1 at the very right, and then we enter here. First, let me perhaps run this function first, and then we'll see what it prints. It will help us understand what is happening. So if we come here, for example, because here I'm doing for two things, let me first maybe erase this guy here for a starter and just run this part. All right, so you see, at the very beginning, this is left and this is right. We swap. What we do is, and then what we do is, we want to, in order to solve this guy, we first need to swap these two, right? And this is what is happening here. And in order to solve this guy, we first need to swap this guy. And in order to solve this, we need to swap these two. So we need to swap this. And in order to swap this, we need to swap this guy. And this guy is the base case, remember, because it's size 1. So once we have solved this guy, we now do the swaps that we were waiting so long to do, and we start just swapping things back again. And this, at the end of the day, we now have something like this, where 9 is at the very beginning, 8 is here, and so on and so forth. So you see, we start here, 0 and 9. We swap them, so 0 is now at the very end here, and 9 is here, and then we still have this bit to do, which is what we consider next, and so on and so forth. And this is precisely what this algorithm is doing, and we're going to see that by putting some breakpoints like we usually do. So let me put one here and another one here, and then let's run this with the debugger. Okay, so this is, we are trying to get, again, left and 9, left and right, and what we do is we move on. We can't solve that directly. We need to solve the other one first, the smaller one first, and so on. We need to solve the other smallest one first, and yet another one, and another one, and another one. But what is the base case? Here, the base case is you don't have like the base case when left is bigger or equal to right, that is our base case, because if left is equal to right, it means that it's an array of size 1. If left is greater than right, it means that it's an array of size 0. So our base case here will prevent us from continuing the recursion if we have if we hit the base case. So and we are close to getting we are close to the base case actually, because at this step left is 4 and right is 5. But soon after this step, left will be 4 and right will be left will be
Left
5.
will be 5 and left will be. They'll
Exactly.
switch places. Left will be 5 and right will be 4.
Exactly. And then we will actually enter this case here. We will actually enter the base case. So if we do that, if I put something here, you'll see we're going to enter the base case. And we are there. We are in the base case now. And that's it. So, and you see, by the time we are here, we have reversed the list actually. The list is already reversed. We can now just move on and move on and move on and move on. And you can see, unlike the other problems, and actually this is important, for example, if you think about the factorial case or the power case, in order to solve the bigger problem, you needed to combine the sub-problem solution. But here we have something particular in that when we are at the very end like this, the problem is already solved. You don't need to combine again because the problem is actually solved already. And this is what we call a tail recursion. A tail recursion, and we're going to see that in a subsequent slide, what a tail recursion means. And it's actually very important to understand that because interviewer give such kind of questions. They want to know how deeply you understand recursion. So you see, yes?
Can I take you back a bit?
Sorry?
Can I take you back a bit?
Yeah, sure.
Combine the sub-solutions. Which
Yes.
sub-solutions are we combining?
If you move back here, or maybe factorial or disk usage, you see here what we are doing. We are getting.
Oh, okay.
You see here we combine.
Yeah.
We get the problem.
Yeah.
We find the sub problems, solutions, and then we combine. For factorial, we do
I
this.
get what I get.
Yeah, but here we actually have nothing to combine because they're already solved. The problem is already solved for us.
So nothing to combine in tail recursion.
Yeah, there's nothing to combine because in your like in a tail recursion, actually we're gonna come back to that. We're gonna have a slide on that. Just stay tuned. It's very well explained in it on a slide of its own because it's very important to grasp the topic. So that's it. That's do you get how this reverse works?
Yes.
It's quite a cool example. I really like this example because it really shows you how like recursion can be hidden in a problem without being very obvious. But you can see here we can solve this problem in a recursive way. So we're going to move back to the slides. Okay. Great. And this is actually the solution that we had earlier. This is it. This is the solution. Now, what is the time complexity and memory complexity? Okay. So what we had, let's draw again our little schema. So we had L like this, defined like this, with a boundary A here and a boundary B here. In order to solve this, we needed to solve little l, which is actually one boundary above and one boundary lower, b minus 1, right? So, and once we have this, so let's assume that the time to solve this guy is T of L. Let's assume that L is size n, right? Let's assume that our list is of size n. So it will be n, right?
Mhm.
So it's T of n. Now, this is the time to solve the big list. What is the time to solve the smaller list? We can say it's T of n minus 2, because each time we reduce the size of the problem by 2, right? Because we don't consider this guy which was here, and we don't consider the guy that was here either. So the size of the problem has reduced by 2. Do you follow?
Yes.
Yeah, so we can have, and once we have solved this guy, all we have to do is those swaps. And swapping is a constant. It's not like if you have a size of n, you're going to swap a variance of n times. It's constant swaps. You just have to do 2 swaps. So it's a constant time. So we can say, given that t of n equals to t of n minus 2 plus a constant time. This t of n minus 2 is to solve little n. This is to solve big L. And this is the swaps. Does the formula make sense?
Yes, it does.
Great. So if
It's
we
linear.
continue like this, what we have is t of n minus 4 plus another c plus the c that we had before, right? And so on and
So
so
this will
forth.
be ON.
Sorry?
This will be ON.
Yeah, exactly. This would be On. You're exactly right. So if we do it, t is t to the n minus 4 plus 2c. And we have like this again. We can say here is 2 to the power of 2, something like that. It doesn't really matter. No, let's write it like this. And at some point, what we're going to have is t n minus k plus k
Yes.
divided by 2c, right?
Yeah.
Does that make
Yeah.
sense? Great.
Yes, it does.
Exactly. And at some point, we're going to have the empty list, which is t of 0. So if we have the empty list, which is what? Because actually this guy, we know his complexity. His complexity is constant. If you have nothing to do, it's just like constant time. You enter the function, you figure out that your list is empty, you return. So it's constant time. So if t 0, so if n minus k equals 0, it means that n equals k. And if you plug that back, it means, what does that mean? It means that we can express t0 times n divided by 2c. And this is a constant time, so it is equals to, you can call this c prime plus n divided by 2c, which is big O of n, because this constant time, this is a constant, this is, sorry, uh, this is a constant here, this is another constant, so it's linear. The slope may be not that steep, but it's a linear problem still. Even though we are decreasing the problem by 2 each time, it's still a linear problem. It's not
Yeah.
a logarithmic problem, because in the logarithmic case, the problem reduces by half each time.
But this is reducing constantly.
Yeah, it's reducing constantly, exactly. And the memory complexity assessment is really, in order to do this, we don't need any auxiliary data structure to keep our data. So we are just bound by the number of stack trace, like number of memory, because when you're computing big L, you need to store something in the stack trace to say, okay, I'm going to come back to you guy, wait a minute while I do little L. And when you're little L, you are 2 steps and so on and so forth up to what? Um,
The final step.
yeah, up to the final step, which is NC, like we saw here from this guy. So it's also linear time, the memory complexity. It's also linear.
So I'm going to, let me ask a question here.
Sure.
Let's say I have an array from 1 to 9, right?
Yes.
And I'm flipping it over.
Yeah.
I've flipped 9 and 1. I've flipped 8 and 2. Technically, when I flipped at the point when I was flipping 9 and 1,
Mm-hmm.
I kept the original array as is. But at the point when I'm flipping maybe, let's say 7 and 3, right?
Yes.
I wouldn't need 9 and 1 in my memory.
Yeah, and you're exactly right.
So
You're exactly right. That's brilliant question, and that's why this is a tail recursion. But the problem is, it's without being too technical. Some compiler actually take advantage of tail recursions and others don't. In Python, in particular, Python doesn't take advantage of tail recursion. And the whole point of tail recursion is that you don't need the sub problems to be kept in memory to solve the bigger problem. You see the point? So you're spot
so
on. You're spot on. So to solve to solve those the big problem, you don't need to keep that in memory. You don't need to keep track of the previous step because actually you won't you never need it anymore.
then
Yeah,
isn't that if Python does not keep it, if Python does not take advantage of tail recursion,
yeah,
I would say isn't that a flaw in how the language was built? It would slow down the whole process. It's basically allocating memory to data that we do not need.
yes, that's correct. That's correct. It's I think JavaScript, some versions of JavaScript take advantage of tail recursion, but Python doesn't, as far as I'm aware.
Okay.
But that's a very good question. It shows that you have perfectly understood the tail recursion and the difference. I'm very, very happy of that. So let's move to the case study number 4. We're almost there. 2 more to go. Do you enjoy this?
it's it's been interesting. I've not done much of data structures and algorithms, but
Yeah,
I'm going to put
definitely.
more time in it.
Yeah, it's important that I mean you're definitely understanding, which is great, which is absolutely great because if you're going for technical interviews with partner companies, they're definitely going to ask you this sort of questions, and we are just getting warmed up. These are still like warmed up exercises. It's gonna get funnier. It's gonna get more difficult as time goes, as time progress. But now binary search. Actually, we had binary search in the previous webinar, but we implemented binary search in an iterative way. And as a teaser, this also is a tail recursion algorithm, and we're gonna see how. So, problem understanding first. Write a recursive function to search k in A and return true if found, false otherwise. Oh, by the way, I should have mentioned that A, let me find the right color. A is an array of integers, an array of integers sorted in ascending order. Ascending order. Okay, with that precision made, let's try to understand this problem. Okay, so let's say A equals 2. We give this example here: 1, 2, 3, 4, 5, and 6 and 7. And we were asked to find if this array contains 7, for example. In the previous webinar, we saw linear search. So what linear search, just to remember what we did last time, linear search will try to, because if you have this and you have your target, the target K that you're trying to search is, let's say, 6. What linear search does, linear search will hope, like we'll start at index 0, trying to find here, is it there? No. I progress. Is it there? No. Is it here? No. Is it here? No. Oh yes, it is. So I found 6. But how many steps do we need to do this? It's 1, 2, 3, 4, 5 steps. We can do definitely better, because imagine this list was a list of size 1 million. You will have needed almost 1 million steps if the target you were looking for was at the very end of the list. We can do much better. And the idea is to use binary search. And the idea of binary
So,
search is, yes,
so linear search is just a simple loop.
yes, it's just a simple loop, a very simple loop.
Okay.
Yeah, that's linear search. But
Mhm.
binary search can take advantage of the fact that normally I shouldn't have forgotten to write this. The ascending here, at least like ascending or descending, but at least the list is sorted. Linear search doesn't take advantage of this fact. And to illustrate this, let's say you had a dictionary, and we all know that in a dictionary, words are sorted from A to Z. And if you're
Mhm.
asked to search for a word that starts with W, you won't start
Mhm.
from A and flip the pages up to the point you reach W. What you're going to do instead, you're going to open your dictionary at the position where you think is quite close to the end, and then if your guess puts you around X, you're going to switch a few pages back, and so on and so forth, up to the point where you're going to reach the position you're looking for. And that's precisely what binary search is doing. So with binary search, what we do is we say this is our list here. We are going first, we're going to consider the middle of our list. So what are we looking for? We're looking for 6, right? So we're
Yes.
going to divide this array into small arrays. So we're going to, this is the middle of our array, right? Once we
Mhm.
are at the middle, we look left and we look right. And we compare, no, we just compare our list, our middle to the target that you're looking for, which is what? Which is 6. We see that the middle is actually smaller than what you're looking for. It means that everything to the left can be discarded, because we know by definition that our list is increasing. So our list is sorted in increasing and ascending order. So if 4 is always smaller than 6, it means that everything that is at the left of 4 is also smaller than 6 by definition. Does that make sense?
Yes.
So binary search actually instructs us to ignore everything, all those things, and only consider this other chunk. So we're going to move, now our array is now this part. Our array is now only this. And we do the same operation. We find the middle. Now the middle, what is the middle? The middle is now this guy. Oh, by the way, it's 6. So we have found our target. How many steps does it take? 2 steps
Two
instead of
steps.
6, right? And as you can see, the size of the problem reduces by half each time, because with linear search, you can say that the search, if you were to do it recursively, it will be a log n, right? because you have to
Mm-hmm.
do a for loop. But here, the size of the problem reduces by half each time. So which is a very big hint that it's actually a logarithmic problem. So now that we have understood the problem, what is the smallest instance of this problem that we can get? Well, I think it's something like this. So we can have a problem of size nothing, of size an empty list. So if A equals to this and K equals to whatever, the problem there's nothing to solve, or we can just return false because there's nothing in our list, so there's nothing to look for. So this is the smallest problem that we have. Now, how can we express this problem into instances of smaller problems? Well, we just saw from the demonstration that we did here that we can, from a binary search perspective, say that n binary search if the problem is of size n can be expressed as a function of binary search of n divided by 2 because we're going to cut the problem in half each time, right?
Mm-hmm.
That's it. And now, how do we combine? Actually, you don't even need to combine because guess what? Combining means that this guy needs this guy to be solved. But remember, when we were here, we completely discarded this. We don't need this
Yes.
anymore, right? This is a hint that is a tail recursion actually happening under the cover. So, because when you're actually searching, when you're searching in this guy, you don't need you don't need anything else than what is in this smaller piece of the array to tell you if what you're looking for is there. So no need to combine for this guy. No need to combine because it's either going to be here or not. So you're not going to merge the solutions given by the the, 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 the the smaller pieces of the problem, like we saw, for example, for the disk usage, where you have like your disk usage like this, and in order to solve the bigger problem, you need to solve the smaller ones and then combine. This is not the tail, this is not the this is a tail recursion. So let's move to the demo to actually see that happening actually. So let's open the PyCharm again. And let's open binary search. But before, actually, let me go first with a bad implementation of binary search, a very bad implementation of binary search, because there are ways to do this very wrongly, and I've seen this way even from very senior people. So let's see what it is. All right, so here is our array that we are trying to search, and what we're trying to do first is to see if it contains 15, which obviously it does, right?
Mm-hmm.
So what we do here, we do very bad binary search, and what we do, we pass in our array A, and it's going to come here. Let me run this so we have something to discuss about. So good. So when we are trying to do, let's just focus on the first one. So when we are searching for 5, because I'm running it 3 times. So when we are searching for 15, we pass in array of A and 15. It comes here, it will be 0 and so on and so forth, and then it will find a mid, it will go left like this, and then what it will do, this is where the bug is. The bug is here, and it's actually the fact that we are doing this. And doing this is creating a copy in the memory for your variable. So you're actually like, when you're doing this, you're passing in to this function, to the binary search, the subsequent call that you're making, an array which is half the size, but it's a new array. And guess what? In order to create a new array, you need to copy the
Memory.
values, right?
Mm-hmm.
You need to copy, and copying is a linear operation. So you may be thinking that you're writing a linear, a logarithmic solution. On the face of it, it's absolutely logarithmic. But by doing this mistake, your solution becomes linear. And this is even more speaking when we look, let me share actually Google Chrome. There we can see the Jupyter Lab, and you will see what I'm talking about. You see my Jupyter Lab, right?
Yes.
Great. Let's share. Okay. So first, let's before even moving to the comparison to the understanding, let's see the comparison. So here, for example, I'm passing a list, like a list of very big numbers, a very long list, and you see it takes 35, 13.5 milliseconds to solve this problem. Whereas if I have a good implementation, how long does it take? 35 microseconds. You see the difference? It's just huge. It's tremendous. So
Mm-hmm.
the good implementation of binary search, you don't have that problem that I was talking about. Because, and here really the problem is that by copying like this, by doing this copy, you're doing a linear operation. So imagine that you had a list of size, that amount that we just passed in here, which is what? 900,000,
Mm-hmm.
let's say 1 million. It means that to solve your problem, this instruction has to copy half the size, which is 500 million items in the memory, which is a linear
Hmm.
operation, which is why this approach is not good. But on the face of it, it looks like binary search, absolutely. Because why? You reduce the size of the problem, you just look at half of the problem size each time, half of the problem. If you have to look on this, on if you have to search on the left, and if you find the element you're looking for, because this else here just means that a meet equals to k, which is our target. So if we found a target, we just return true. If we don't find it, if a meet is lower than k, we search on the right. It means that, like we saw in our example, everything
Mm-hmm.
to the left will definitely be smaller. So we just keep looking on the right. And by looking on the right, it means that we move left to wherever meet was plus one. And that's it. So it looks like binary search, but this is a bug. This is definitely a bug. And you can see it very clearly when we time it. You see it takes 13 milliseconds versus a good implementation, which will just take 35 milliseconds. And let's look at the good implementation. Let's see how it looks. It makes uses of helper function. Once again, always important to make sure that you write your, like, you consider using helper function to ease the problem for you, to make the problem easier for you. Because the person asking you to write, and by the way, these verbals are not necessary, it's just for us to see what is happening. Like you can see here
Mm-hmm.
what is
Yeah.
happening. Yeah. So if someone asks you to write a binary search function, he doesn't want to know about your implementation details, about the fact that you're actually using left and right to control um, the size of the search domain where you're looking at, because left and right defines the boundaries where you're actually trying to find the target K. So when you define your helper function like this is our base case. Our base case is when left is bigger than right. And like we saw in another problem, this means that it's an empty list. Because if left has moved and moved and moved to the point where it crosses and passes right, it means that we have an empty list. So in that case, we return false. So because target can never be in an empty list. Well, now we solve the sub-problems. We solve the sub-problems. And for that, what we do, we find the middle. And by the way, this way of finding the middle is clearly explained in the previous webinar, why we do it like this. But because we could have written something like this, instead mid equals to right plus left divided by 2. And this will work fine. Minus a little caveat, a little bug, which is explained in the previous webinar. So, and here, this is it. This is really all you have to do. And it solves the problem. It's efficient. If you don't see it, if a mid is lower than your target, it means that you just have to search, keep looking on the right. And keeping looking on the right means shifting left to wherever it was before. So left was here. If you look at these prints, here we're looking for 15, right? It means that we're actually going to shift to look left, because when we are here, middle is this guy here. And when we're going to do mid, we're going to, so right is going to move to the left, because 15 is actually smaller than what was on the middle. So we now put right here, which is precisely what is happening here, because this is 0, 1, 2, 3. Yeah, so now right is here. It means that mid was this, and so on and so forth. And you keep iterating like this. And you can see for the case of k equals to 100, obviously 100 is not here. We are just going to return false. And for a case of 51, we're going to return true because it's here at the end. So this is it for binary search. So I'm going to move back to the slides one more time.
Hold on.
Yeah, sure, absolutely.
Let's say k was equal to 8 in this particular array.
Do you see my screen?
Yeah. I'm seeing Jupiter.
Okay, good. Yes.
Let's say k was equal to 8.
Let's say k was equal to 8. Yes, let's search for that. Let's search for k equals to 8.
I'm seeing your screen, but nothing's changing.
Oh, okay, let me, I know why. Let's see. Okay, do you see now?
Mm-hmm.
Great. So you're looking for 8.
Yes.
That's it. So it's going to give you this. It's going to give you true.
But it will ignore the previous 8 or
Yeah,
an index one.
it's going to return. And actually, if you want to understand this better, we can move to the previous. Let me share the pie chart. Okay. In the previous webinar, we had this guy. Oh, where was it? Actually, I will share my screen and you see what is happening. Great. I'm just opening the slides for the previous webinar because this was very well explained there. Okay, I'm just looking for the right page where we discussed that. Okay. So Here, actually, this is precisely your question. We had binary search in the iterative way, but we also had the variant of binary search in the first webinar, which was to find the first occurrence. And if you look at this comparison here, binary search iteratively will return mid. So it will return the first occurrence, which is this guy here. Binary search, if you're looking for 8, binary search will stop here. And this is why you get this 4, right?
Okay.
But if you're looking for the first occurrence, it means that you don't want to return as soon as you find the first occurrence. As soon as you find, like, if you're doing binary search, it means that definitely you're going to see this guy first,
Mm-hmm.
right? You're going to meet this guy first. But
Yeah.
nothing tells you that it's actually the first instance of 8 that you have in your list. So unlike binary search, which will just return as soon as we find the first time, first occurrence search keeps looking on the left here, right? And this is the only
Okay.
difference between the two. Does that answer your question?
Yes, it does.
Yeah, so if you're asked to find for the first occurrence, you don't have to return as soon as you hit the target. Just keep looking on the left. And keeping looking on the left means you keep shifting right leftward, which is what this diagram is showing here. So you keep moving right, up to the point where you find what you're looking for. Great. So let's close this. We have had the coding time for binary search. Now, like we discussed, we saw the very bad approach, and we saw that this was actually the problem. This was the problem maker here, because this is creating a copy. It's actually bad time and memory wise. It's not just bad time wise, because it's creating a
Mm-hmm.
copy of size n divided by 2. So it takes memory n divided by 2 plus memory wise and time wise n divided by 2. So it's a very bad approach, and you will see this very frequently. And if you do this back, it's not good for an interview, because it shows that you don't know how memory management works in Python and stuff like that. So this is how you have to do this. Use pointers, left and right pointers, and a helper function to help you to define the search space instead. This is very important. Now let's talk about memory complexity. We already almost touched on that when comparing the bad and the wrong one, but it's important to do it in a structured way. And we're going to do this just for the good approach. So we had binary search of A, K. Let's use a different pencil. So we have binary search of A, binary search of K in A, and let's say A is of size n. Size of A is n, right? You saw that in order to solve this is dependent on solving a problem of a smaller size, which is binary search of a smaller a and k. And the size of that smaller a, it was n divided by 2, right? Because each
Mm-hmm.
time we cut the problem by half each time. We cut the problem size by half each time. So, given that, we can write a formula, a recurrence formula, which is how it's called mathematically. Recurrence formula will be T of n equals to T of n minus divided by 2 plus a constant time. And the constant time is the time to actually, when you have reduce the problem by half, like this.
Mhm.
When you reduce the problem by half, you still have to check. This is taking like constant time, these comparisons here. So you have one comparison, potentially two, and maximum, like, yeah, one or two comparison in order to decide what to do next, right? So when your
Okay.
problem is divided by half like this, you have one or two comparisons, and those and also maybe this is taking also constant time. So this is C, it's a constant, you can call this C1. This comparison is taking maybe C2, this comparison is taking maybe C3, and altogether the amount for a constant, general constant that we can call C. And when you have this problem, let's say you have, in order to decide what to do next, the next step will be you have constant time operation. And once you have decided what the next step is, that next step is a smaller problem of size n divided by 2. And that's how that recurrence formula comes. So we have the t of n, first the c, which is what to do next. What to do next. To do next. And this guy is a side time to actually do that next step, time of next step. Does that make sense? So,
Sorry, I was muted. Yes, it does.
yeah, great, great, absolutely. Great. So, and you see, it looks like what we saw earlier. So, we have now like this. It looks like what we had earlier, which is t, oh, wait, t, we can continue reducing this, n divided by 4 plus c plus c, which is what? Which is nothing but t to the power of n 2 plus 2c's. If we carry on like this, we have t to the power of n divided by 2 to the power of k plus kc, right? Now, we are going to reduce the problem by half and half and half and half. Up to some point, we're going to have a problem of size 1. At some point, we're going to have a problem of size 1. And when we're going to have that problem of size 1, we're going to be at something like this, t to the power of n, 1 plus something here times c. What is that something? Well, in order to find that something, we equate this. Say, let's say 1 equals to n 2 to the power of k. It equals to, equivalent to saying that n equals to 2 to the power of k. And if you put the logarithm on both sides, we get n equals to log 2 of k. Oh, sorry, it's the other way around. K equals to log of n. And that's it. And that's how we get it. So we're going to write now it's equals to t of 1 equal to t of 1 plus log of nc. And that's how we get the final time complexity as a variable of n, which is log of n. Does that make sense? So this is how we actually compute the time complexity. And again, like we saw, even this is a tail recursion because actually we don't need to keep track of what was happening. We don't need the sub steps. to solve the big problem. We don't need the sub-steps to solve the big problem. It's a stale recursion. So technically speaking, we don't need any memory, additional memory, but because we are using the stack trace and Python doesn't take advantage of the tail recursion, we are going to be having log of n as well as memory complexity. Because at each step, we need to keep track of what is it that we have to do in order to solve the problem, even though technically we don't need it. So that is it for this part. And I think, do you have any question for this?
Not at this time.
Great. So let's move to the very final problem in our webinar, which is Fibonacci. Fibonacci. In the face of it, it looks very, very simple, but really it's a knockout question. Many people get the job denied, refused, because they fail to give a proper implementation of the Fibonacci. And I myself, at the beginning of my career, got rejected because I failed this. So it's very important to get this right. Like I said, on the face of it, it looks very simple. Very, very simple problem. But there's something going on. There's something going on for this one. So I'm very excited about this problem. Let's see what it means. So once again, problem understanding. When you're asked to do a problem, you may not know what Fibonacci is. Perfectly okay to ask your interviewer what it is, and he may say something like, Fibonacci is the function defined such that it's equal to 1 if n is lower or equal to 1, which is actually 0 or 1, and fib of n minus 1 plus fib of n minus 2 otherwise. So that's it. That's the definition of the Fibonacci function. It's quite simple, and we can see from this definition that it's very recursive by nature. Like by nature, the problem is recursive. So, and also the base cases are even given to us. So the base cases are simple, is n equals 0. You're going to return fib of 0 equals what? 1. And the other base case is n equals 1. You're going to return fib of 1 equals 1. So this is how Fibonacci is defined. Oh no, sorry, it's equal. No. What am I doing? So it's equal to fib of 0 is 0. So it's equal to n if n is lower or equal to 0 or equal to 1. So fib of 0 is 0, fib of 1 is 1. That's how it's actually defined. That's the Fibonacci function. So how are we going to break this into sub-problems? Well, the sub-problems as well are given to us. The sub-problems are defined. So we know by definition of the problem that in order to solve fib of n, we need to solve both fib of n minus 1 and fib of n minus 2. That's how we define the problem. Well, once we have the sub-problem solved, how can we combine the sub-solutions to those sub-problems in order to get the actual solution that we're looking for? Well, that too is given to us, this plus here. So once we have these two solved, what we have to do is simple. We just have to sum fib of n minus 1 plus fib of n minus 2, and this will give us fib of n, Fibonacci of n. So far, so good, right?
Mm-hmm.
Great. So let's look at implementation, the naive implementation of the Fibonacci. Great. So I call this naive Fibonacci. Let me close all the other ones so far. Great. Naive Fibonacci. Like I said, on the face of it, it's a very simple problem. If I run this, we can see. Let me actually comment these two guys. And let's just run Fibonacci of 4. You see here, it's exactly what we just defined. It's like the definition, really. So if it's the base case, you just return. We solve the sub-problems. Previous Fibonacci is Fibonacci of n minus 1. Previous of previous Fibonacci is Fibonacci of n minus 2. And then we combine the sub-solutions. That's it. Very simple problem. But something very interesting is happening here. Let's see by looking at what is being printed here. Look, we are computing Fibonacci. I think it will be more speaking, looking at Fibonacci of 5. Let me run Fibonacci of 5. You see what's happening here. When we enter that function, we first want Fibonacci of 5. But in order to get Fibonacci of 5, we need Fibonacci of 4. And in order to get Fibonacci of 4, we need Fibonacci. In order to get Fibonacci of 5, you need Fibonacci of 4 and Fibonacci of 3, right? So we need both this guy and this guy here. And when we are computing Fibonacci of 4, we need Fibonacci of 3. But Fibonacci of 3 was already computed here because all these steps here are actually meant to compute Fibonacci of 3.
Mm-hmm.
So when we are computing this Fibonacci of 3, here is actually doing double work because we did it before already. And this is, if you understand this, you understand what is the problem with this approach of computing the Fibonacci numbers. And in order to
Yeah,
make,
repeating.
sorry? Yeah, we are
We
repeating, we are doing the same thing many times, many times, over and over again. So if we put some breakpoints here to understand what is going on even more clearly, we see what we are trying to do is compute Fibonacci of 5, okay? We're gonna enter, in order to get that, we need Fibonacci of 4, right?
Mm-hmm.
We need Fibonacci of 3 to compute Fibonacci of 4. So far, so good, and so on and so forth. And then once we have solved Fibonacci of 4 or Fibonacci of 3, we now need to solve it again, and so on and so forth. And you can see we compute Fibonacci of 4 many times, Fibonacci of 3 many times, and this is not a good approach because when we will talk about the actual complexity, you will see we will draw a tree and it will explain very clearly what is actually happening. But like again, like we saw here when running the function, it's computing the same thing many times. And if we do it for Fibonacci of 10, you will see it's even worse. So if we do for Fibonacci of 10, you see it's even worse. Like look at everything. We do Fibonacci of 9, we do it here. Fibonacci of 8, I think Fibonacci of 8 we compute many times. So this is Fibonacci of 8 that we're trying to find. And we're also trying to find it somewhere here, somewhere here. Again, as well. Same thing for Fibonacci of 7. We get it here. And we also try to get it somewhere above here and so on and so forth. So at least, at the very least, we are computing the same thing twice. For some others, we are computing them many times. So Fibonacci of 1, we compute it here, we do it here again and again and again. So there's definitely something happening here, which makes this very non-efficient. And to make that idea even, to draw that idea even closer home, let's look at the Jupyter lab and compare the time complexities. So here I run Fibonacci of 4. It took, do you see the Jupiter? Hi, you see the Jupiter?
Mm-hmm.
Great.
Yes, I
So
do.
yeah, if we run the Fibonacci of 4, you see what's happening here. It takes 1 milliseconds. We are already at Fibonacci of 4, and it takes 1 milliseconds. Fibonacci of 40, I ran it before, it takes 52.9, almost 53 seconds. So it's a dramatic increase. Fibonacci of 4, 1 milliseconds. Fibonacci of 40, 60 seconds. So it's almost like, wow, if I go to Fibonacci of 100, it's going to be, I would have to wait for days. So there's something really, really bad happening, and we're going to see what is happening in the closing remarks. So for now, let's just look at the time complexity. Unless you let's look at the time complexity for this problem. So let me share again the slides. Great. So this is the problem that we had again. Here you can see for Fibonacci of 40, it takes 54 seconds in a different time, at a different occasion when I run it. So what is happening? Time complexity, and this is very important to understand. So let's take a simple case. Let's try to find Fibonacci of 4. To get Fibonacci of 4, what do we need? We need Fibonacci of 3 and Fibonacci of 2, right? While computing Fibonacci of 3, we need Fibonacci of 2 and Fibonacci of 1. When computing Fibonacci of 2, we need Fibonacci of 1 and Fibonacci of 0. This is a base case. This is a base case. This is a base case. This is not yet a base case, so we have to break it down, continue breaking it down. Fibonacci of 1 and Fibonacci of 0. So you can see that we are repeating the same problem. So for example, if I draw again, this chunk here, this whole tree is all computed here and here. So you can see that we are computing Fibonacci of 2 many, many times. And 2 times when we are doing for Fibonacci of 4. Now imagine for the case of Fibonacci of 10, for example. If let's say this was a big number, it means that if I erase all these, and I draw again Fibonacci, let's come back to actual numbers, to actual variables. Fibonacci of n, we need, what do we need? We need Fibonacci of n minus 1 and Fibonacci of n minus 2. And in order to compute Fibonacci of n minus 1, we need Fibonacci of n minus 2 and Fibonacci of n minus 3. And this guy here, we need Fibonacci of n minus 3 and Fibonacci of n minus 4. And if you see, you can already spot some repetitions happening here. You see that this guy, you're computing it here and here, and that this fig tree, you're computing it here and here and so on. So if you unroll the tree even further, you're going to get even more repetitions. Guess what? If you go, for example, for this guy, it's going to be fib of 4 and fib of n minus 4 and fib of n minus 5. we get yet another repetition here and here, and so on and so forth. So you see, something is definitely happening. We are repeating the problem, same problem over and over. Said that enough times. So now let's see what is the time complexity for this problem. So from the graph that we just draw, we can see that, actually I shouldn't have erased it. I would maybe let me come back.
But I followed.
Yeah, I'll just actually just move it. I'll just move it to the right, like this, and then I just wanted somewhere to write. Great. So it means that if you're looking for time complexity of n, how can we write it down? It's like we can say that to compute the time, the Fibonacci of the time it takes to solve Fibonacci of n. In order to solve Fibonacci of n, we need to solve two Fibonacci's of Fibonacci of n minus 2. So this time is bigger than 2 times the time it takes to solve Fibonacci of n minus 2, right? Because to solve this guy, we need to solve this guy twice, once here and once here, right? This is Fib of n minus 2. We need to solve this twice, right? So we don't take into account this part because what we're trying to do for this is to find a lower boundary and an upper boundary to kind of find like a boundary. So we're trying to get something like lower complexity, Tn, and bigger complexity, like this. So we're trying to find an uppercase and a lower bound and an upper bound, because it's not very simple to find like the direct complexity. So here we have already a lower bound. We know that T of n will be bigger. We know that T of n will be bigger than this. And we also know that it will be smaller. T of n will be smaller than 2T of n minus 1, right? Because the time it takes to compute Fib of n minus 1 is smaller than the time, it's bigger than the time it takes to compute Fib of n minus 2 here. So we can assume that we have these two conditions that are met. Are they clear?
Yes.
Yeah. So once we have these two, we have an uppercase and a lowercase boundary, right? Now it's going to be this. It's going to be pretty much the same like what we did earlier. So we can say actually that now it's equal to. We can say in order to ease the work that we have to do, let's consider the uppercase, for example, T of n lower than 2 of T of n minus 1. It means that it's rootly equivalent to 2 of minus 1, given that we add a constant time to it, like some constant time. So we can approximate it like this, and once we do it like this, we can continue, we carry on, we say it's now equal to what? It's now equal to 2. Now we also like break this piece down and say it's equal to what? T n minus 2 plus another constant plus the previous constant, right? Great. When we continue, it gives us 2 to 2 n minus 2 plus 3 c's. And then we continue, we say it's 2 to the power of, n minus 3 plus c plus our original 3 c's that we had earlier, which will now give us, oh, what am I doing? Feel like I'm missing something. Oh yeah, I'm definitely missing something. I should have had 2 here because the formula is like this. So t of n minus 1 is 2 times t of n minus 2 plus a constant. So normally I should have had 4 here instead of 2. The same thing, 4 here and 2 here inside, like this. Now,
Okay.
what I have here is what? Is 8, or I can even have like 2 to the power of 2, which is even better. I can say 2 to the power of 2, 2 to the power of 2. And when I'm going to multiply, it's going to be 2 to the power of 3 times tn minus 3 plus 2 to the power of 2 plus c plus 2 to the power of 2 minus 1c. I'm going to ignore those factors because really we are caring just about the biggest factor anyway. So it's going to be this, and so on and so forth. If I keep doing that, at some point we're going to have 2 to the power of k t n minus k plus let's say 2 to the power of, wait, just use c. Okay, so let's say, I think, I'm not sure if I had the math exactly right, but it's something like this. Okay, so this is what we have actually so far. Is it? I think it's something like, wait, no, it's like this. Wait, let me write it down correctly. Okay, 2 of k minus 1 times c. Okay, so once we have this, we do like we normally do, like we usually do, like we have been doing so far. We say, okay, so we are reducing the problem. We're reducing the problem. At some point, we're going to reach a problem of size 0, because here we are reducing by reduction, not division. So at some point, you're going to reduce, and it's going to be t of 0. So at that point, it's going to be 2 to the power of 0 to the power of, sorry, to the power of k. No, sorry. It's going to be 2 to the power of something, t of n of 0, 2 to the power of that something again, minus 1 times c. And we are looking for that something. And to find that something, we plug, well, 0 here, which gives us n minus k equals 0, which means that k equals n. So that something that you're looking for is k, is n. So we have here 2 to the power of n t0 plus 2 to the power of n minus 1 times c, which is the time complexity of our problem. And you can see it's an exponential complexity, because all this amounts to big O of 2 to the power of n, which is exponential. And these are the worst possible, one of the worst possible complexity that you can have. So Fibonacci, when implemented in a naive way, even if on the face of it, it looks like a very simple thing, look at this, it's like very innocent, but it's an exponential problem. And that's why it grows so fast. So from 4 here, with just a couple of microseconds, to 40, we move to almost 1 second. That's because the problem is exponential. Unlike a linear problem, or like a logarithmic problem, this grows really, really, really fast. So if you were to draw the plot like this, you put n here, you put t of n here, you have a complexity plot that is something like this. It grows very quickly, and that is exponential growth. And you definitely don't want to have your algorithms growing this fast, because it means that you cannot solve big problems. Because if it was 400, you have to wait for like months, possibly years to solve the problem, if possible. So there must be a better way, and that better way we are going to discuss it when talking about some closing remarks regarding recursion. But before that, do you have any question on Fibonacci?
None so far.
Great, great, great. So let's look at some closing remarks on Fibonacci, on recursion. The first one is recursion the recursion error, maximum recursion depth exceeded. You saw when we discussed the time and memory complexity, we kept saying that we have something to store when we are computing the sub problems, like when we are doing factorial of
This
n.
would be
Yeah, we need to store something first. Need to store here and store here when you're doing factor of n minus 1. And we are storing this in a stack. So we have
yes.
something that we call a stack trace, and we store that in a stack. But that stack has a limit. And you can see here, for example, in Python, the stack trace limit is what? Is 3000. Obviously, you can change this. You can do sys dot let me do that correctly. Sys dot set recursion limit and increase it to, let's say, what 1 million. But that's not ideal. It means that you're going to have a stack trace, a stack of size 1 million, or 10,000 or whatever. It means that you're going to use memory, because that stack is the memory that you have to use to keep track of where are you currently at in your attempt to solving the recursive problem. So you store states of partially solved problems, so that when you have the sub problems, you can come back later and combine the solutions of those sub problems to solve the bigger one. So yeah, this is something to be careful about. You see here our factorial function that was working fine, but as soon as we pass in 3000, we have this maximum recursion depth exceeded. Same thing for the power and for all the other ones. So very important when you're writing a recursive algorithm to take into account the fact that by nature recursive algorithms use the stack trace this way to store the partial solution problems in memory. So yeah, which is a very perfect transition for tail recursion. Tail recursion, we already touched on that, but again, just to iterate one more time. If we were to solve the problem that we solved earlier, which is disk usage, without tail recursion, this is what actually Python is doing. So let's say this was 1 MB. This was another 1 MB. And this one here, I'm not going to consider the sub children. I'm just going, and this was 2, and this was 3 MB, right? So without tail recursion, in order to solve this guy, you need to have the individual solutions. You need to have this and this and this and this. And then once you have them, you combine to find the solution of the bigger problem, which is this guy here. Both, you can convert that into a tail recursion problem, such that you don't need to store each of these individually before actually solving the bigger one. And you can do this by having, like you can see on this implementation, an accumulator, this accumulator here. So what that accumulator will do is, let's say you're trying to solve again this guy here, and instead of keeping track of the smaller pieces one by one like you do here, what you do with the accumulator instead is that, okay, I will start by computing this guy and I will have my 1 MB. When I'm here, in order, I will tell this guy that I was 1 MB. So he will just append his size. So it will be my size plus your size so far, which is what, 2 MB.
2 MB.
So at this point, I actually don't, I can discard this guy, right? Because his
Yes.
size is already taken into account by because he has given his size to whoever needed it already, to the next guy who is going to be computed in the stack trace. So, and this guy is going to do the same. So when it computes like this, it's going to tell to this other guy up here that, okay, I was 2 MB. So you don't need me, you just need my result. So just add your result to mine, which will be 2 MB plus his 2 MB, which will be 4 MB. And same thing, you can discard this guy and it will just pass his result to this other one here, and it will be 7 MB. And that's how you accomplish a tail recursion, by having an accumulator which just runs and you pass it to everybody. You can see here, if you look at the difference with the previous implementation, I should have really printed the two solutions here, but we can quickly move back to it. So you see how it looks. Again, let's quickly open that. Okay. Where is that again? Okay, 1 sec. 1 sec. 1 sec. Great. So this is how it looks. It looked before. So we will compute the children's size and just just return. So you see here we need a combine step. We need a combine. We actually need a combine because we gather the children's size one by one. So we get the size of this child here like this. So we get this the size of this child, we get the size of this child, we get the size of this child, and then we sum them together with this plus this plus this plus this, and then we need to sum it to the size of the actual parent folder, and then we need to return it. So you see, we need a combination step. Whereas with the tail recursion step, with the tail recursion approach of doing things, we don't need that. We don't need that extra combination step because we do it in a clever way that allows us to never need to do it. So instead of doing it that way, we have this so far variable. So when I'm computing the Fibonacci, the size for a given children, I pass in as well to whoever is going to need it next at the next step, so that he just adds his sum. And this is what we just drew here. This is what we were doing here. So when I compute mine, I pass it to the next guy. And this is what he's doing here. So I compute mine like this here. I compute mine here first. And then let's say I'm at step 1 of the for loop. So I'm at step 1 of the for loop. I'm going to compute this guy, right? I'm going to compute my size here. And when I'm going to be at, and it will be 1 MB, right? It will be 1 MB. When I will be at step 2 of the iteration, I'm going to get the next child, which is this one here. So I'm going to get this. I'm going to say, okay, give me this usage tail recursion of what? Of templates, of the folder called templates. But take into account the fact that tests already has 1 MB. So use 1 MB as the size so far. And it's going to do the same when we're going to be at the third step. It's going to say, okay, I'm going to compute. I know that, okay, I need to compute the size of templates, and the size of template is the size of test plus the size of template itself, and so on and so forth. So you're going to do the same for lib, and so and really this means that you don't need this combination step anymore. You don't need this, and that
Yeah.
helps you to have a day recursion implementation of the same algorithm. And like I said, tail recursion are good because if you have an interpreter, a compiler that takes advantage of it, it will be memory efficient. But we don't have that in Python. But some languages actually have a compiler that is optimized for tail recursion. So let's move to the next and final remark, which is memoization. Take advantage of memoization. Look at what we did to our Fibonacci, which was time exponential. Remember, 40 was giving us 53 seconds. Now it's giving us 28 microseconds. Oh, wow. What have we done? Such an improvement. And what we did was very, very, very simple. We used a memory, like a, like a step to cache whatever is already computed so that we don't repeat it anymore. And you can see it here and here and here. These are the only things that we added. Everything is like it was before. We have our base case, we have the subproblems, we have the combination of the subproblems. Everything looks the same, but the complexity is dramatically increased. It's now linear, as we will see. So remember, when we had our Fibonacci, we were computing the same thing many times, but they were not computed all at the same time, right? Because see, like this guy, when we're trying to find fib of 2, the first time we try to find fib of 2 is here, right? Fib of n minus 2 is this time here.
Yes.
So we are still at this level. What about us caching this in a dictionary and saying, okay, memo of n minus 2, this is a dictionary, will be what? Will be whatever will be the result of this. So that when we are now at this step, so this is step number 1, we can say 0, 1, and 2. What about like when we are at this step, instead of recomputing it, we first check inside of memo if it's already there. If it's there, just return. You don't have to unroll this tree on its own to find the solution. If it's there, just give me the answer. Don't repeat what you have already done. Sounds like simple, very obvious. So, and this is what we call memoization, or if you want, dynamic programming. And we will have a webinar on dynamic programming on its own because it's a very, very, very powerful technique of optimizing algorithms. For Fibonacci, it may seem quite obvious, but sometimes it's quite tricky to see how to improve an algorithm using dynamic programming. But it's a very powerful technique, and you can tell by the optimization that we just did here. We moved from 53 seconds to 29 microseconds. Oh, wow. Such an improvement. It's really, really, really a big gain. Big, big, big gain. So what is happening, like we said, when you enter the memoized version, you first check if whatever you're trying to access in that memoized version, if the parameter, the Fibonacci that you're trying to look at is already in the memo, well, we don't have to do these things. We just return, which cuts completely several places of the tree that we normally would have had to follow. And you can see it here in the prints. You just compute Fibonacci of 4 once, Fibonacci of 3 once, Fibonacci of 2 once, Fibonacci of 1 once, Fibonacci of 0 once, which implies that is big O of n. It's linear time now. So
Yeah.
that's how, by doing this, we have reduced something that was exponential into, you can see again here, from this trace, you can see here we needed Fibonacci of 3, or like Fibonacci of 2 many times, but here is just once. And yeah, this is how you reduce something that was exponential into a linear time algorithm. And one of the webinar will be specifically dedicated to dynamic programming, and we're going to cover that in the very depth because it's extremely important to understand how it works. And yes, that's it. Any question?
No.
Great. So we have reached the end of this webinar. Hopefully you learned something new. It wasn't too fast paced. Hopefully it was worth your time. And the next webinar will be again on algorithm data structures. We're going to cover hash tables. We're going to have an introduction to dynamic programming. And the second part will be on system design. We're going to see REST APIs, a case study on Django REST framework, and we're going to also look at caching with a case study on Redis. And the next webinar is not next Saturday, it's the Saturday after that. So it's on the 16th of November, same time, same hour, same place. Thank you for your attention and see you later. Thanks.
Could
Yes.
you share the recording?
Sorry?
Could you share? How will I get it?
Absolutely. Everything will be shared. Everything will be on the internet by today or tomorrow morning. Everything will be on the internet. The slides,
Okay.
the code, the video, everything.
Okay, thank you.
On the website. Great. Bye.
Cool, thank you for your time.
You're welcome. My pleasure. And see you. Bye.
Bye-bye.